Hello and welcome to my talk for this year's DebConf, DebConf 21, titled as Probing into the World of Data Science. So before I start, a little bit about myself, the speaker. So I'm a 20-year-old student studying computer science at the University of Liverpool. I'm currently on my industrial placement here as a data scientist. So I first started, in the Debian world, my first installation was when I was roughly 15, but I didn't start contributing until 2019, and I essentially entered through the Debian Met team. And this is still the team which I focus predominantly my packaging efforts in. But this isn't the only team I contribute in. I also contribute in Python and R packaging teams. So as of July of last year, I became a Debian maintainer, and my Debian developer status is in the pipelines. So, what is data science? Before I go into my talk, I think it's really important to address the topic itself before explaining different elements under it. Data science in itself is quite an umbrella term. It's a broad term. And within that term, there are different fields such as data analysis, machine learning, and statistics, which go hand in hand with analysis of data. And the aim is to essentially find or extract some meaning, some pattern, or some semantic structure or value in the data itself. So more on that as we go further. And indeed, those that practice data science are called data scientists themselves. So what is a data scientist's typical workflow? The workflow looks like this. We start by acquiring the data, and upon acquiring the data, we wrangle the data. And wrangling can be thought of as the action of reshaping the data, modifying the structure of the data, splitting the data, essentially touching the data in a way where you do not introduce bias, but you get it close to a perfect structure that you need so that you can push it further down into your architecture or your pipeline. And indeed, data exploration, as the name suggests, goes hand in hand with data wrangling. As you explore, as a data scientist, as you explore the data and you get to know what the data is and the sort of structure behind it, you may find the need to perform further wrangling. And the end goal is to, of course, model your data modeling. But modeling doesn't only mean visualization of the data. It can also mean developing some sort of machine learning model from a pre-existing or your own architecture, so that you could, for instance, classify data that's never been seen before by the model itself. In this talk, I'll be discussing about performance-related issues, and one of the key issues when it comes to performance is indeed the task of machine learning, which in itself is quite heavy, and you will see why. And one topic that's quite fun to talk about is neural networks themselves, which I think they're fairly easy to understand. So, neural networks, what are they? Well, neural networks essentially contain neurons, but in mathematical terms we call them perceptrons. And essentially, they mimic the neurons in the brain. So given some arbitrary input or inputs, we fire when a certain criterion is met. And this is what a perceptron looks like. And indeed, we can see three inputs, x1, x2, and x3, being fed into a summation function. And in this summation function, essentially you have your weight vector w, which you're trying to learn, because the goal is to learn the value of the weights in the vector w. And indeed, when you transpose a vector and you multiply it by x, it is essentially saying w1 x1 plus w2 x2 plus etc. And the result, the resultant value is net1, and this activation function is actually a discrete output. So if the value of the net1 is strictly less than 0, then we don't fire. Otherwise, if it is non-strictly greater than 0, we fire. And indeed, this idea of the activation is not just bounded to the simple example. The beauty of the beauty of neural networks is that it is adaptable, both mathematically speaking and concept-wise. So say that you wanted the output to be of a probabilistic output, which actually comes very handy if you have multiple classes and you construct interconnected neurons, or perceptrons, should I say, and you can get sort of confidence values of each class. Then you would simply use a sigmoid function for your activation function, which would essentially squash down the value to be bounded by between 0 and 1. So essentially it's probabilistic. You'll see why I've introduced this slide when I do talk about complications and performance. So as I've said, the goal of learning the values, the goal is to learn the values in the weight vector W. But for most in-life applications, we don't really consider one single perceptron. Especially when we look at the XOR case, a single perceptron cannot solve this. But we indeed can use the idea of perceptrons to create interconnected layers of perceptrons to form what is called a neural network. And you have different derivatives of neural networks. You have you can apply it into the concept of deep learning. You can have interconnected layers. In this sense, we assume to be fully connected, but there's different variations. Quite a good heuristic to list is the number of trainable parameters dependent on the number of input units and the number of output units. So for a fully connected neural network, this is essentially this, which is actually a useful hyperparameter to know, because it gives you an understanding of how of what the growth function is given how the number of perceptrons in your model changes. And essentially, this growth factor is relative, or actually dependent on, it actually reflects onto the number of parameters that you need to train and learn. So there is of course more to this. I have not discussed how learning happens. Learning is indeed the most costly thing, both hardware-wise and in terms of time. I won't cover forward or backwards propagation algorithms in this talk, but if you're interested to learn more about it, then please consider reading about them and how gradient descent can be used to find, hopefully in steps, a global optimality. That is the hope. Now, what I mean by costly is that it can both be time and space heavy during the computation of learning the weight vector. So for this talk, the assumption is that I will be focusing on two languages, that is R and Python. And this is just to remove any sort of abstraction. With any set task that exists, there is a lot of, there is a list of complications to be on the lookout for. So as a data scientist, you're going to spend most of your time wrangling the data and preparing it itself, and you use various stages of techniques such as data discovery, which goes hand in hand with exploration, structuring, validating, cleaning, and enriching. Second point is hardware constraints. Some data sets can actually be very huge. Hardware and time might be costly. More apparent if you're training a machine learning model, which is what I mentioned in the previous slide, which you got a glimpse of. And our third and final point is the authenticity of the data. So can we confirm the integrity of the data? Is it a reputable source? Are there any redundancies? Can we be sure that no errata or errors exist in the data? And so we will have to look back into data wrangling or the origin of the data, but usually in most cases data wrangling and preparing the data before you feed it down your pipeline suffices. But there is one crucial element which I didn't mention, and that is, what question would you like answered by analyzing or modeling the data? When you're given the data set, even if you know what the different variables are or the predictors are in that data set, do you know what you're doing? Do you know what you're trying to achieve by analyzing the data? Is there a question that you want answered? So essentially, can we find some relationship between some variables? That is usually the question that you want to answer. Because perhaps researchers are looking for some sort of correlation or relationship in the data, but also in addition to this, finding some relationship between variables might actually aid with answering this arbitrary question. The discovery can also aid with doing predictions and training a machine learning model which could classify or predict on unseen data. But we could also do regression tasks as well. So, remedies. For all the issues I've listed, there are remedies. First one, as we mentioned, data wrangling. We could look into introducing automation into our pipeline. Automation in the sense that we use machine learning because we assume that the data feed that's coming in is unseen data. But we also assume that perhaps it's in the same sort of shape or structure and it's not too dynamic. To which in that case we could use a tool like Automunge, which I've used before. But also you could look into introducing some common workflow if the data is the same. And an interesting idea, maybe we can use the common workflow language to further aid with how data passes through each step of a pipeline. Machine learning can be used to learn for the patterns, which can sometimes be very difficult, especially with high-dimensional data. Hardware constraints. We could use some sort of data generator. A data generator can be a function that feeds subsets of the data set, which is essentially feeding data in batches. So not all of the data set is going to be in memory. We could also look into using non-commodity hardware such as HPC. And HPC in itself can use a job scheduler like Slurm. And fortunately, Slurm Workload Manager is in Debian thanks to the HPC team. The predominance of computers and its digitization has fortunately lowered errors in data aggregation analysis than when it was previously possible doing it by hand. And our third point is data authenticity. We could look into using the GPG tool, maybe digitally signing our data, but this also could relate to the actual integrity of the data itself. So we may have to refer back to wrangling or the origin, which is the source of the data. So, how do we actually perform the analysis, digital analysis of the data? Now this is the fun bit. We could use a language like R, which is a statistical programming language. Debian contains 1,116 R packages in Bullseye to this day. Actually, to the date that I made the slide, which is early August. And according to UDD, some of the most important R packages in data science, such as the dplyr and the tidyverse, they exist in Debian and are both very useful when it comes to data wrangling. And the way I aggregated this is by doing pattern matching in some of the UDD SQL queries I ran. So indeed, CRAN is both high volume and high velocity regarding its package, with around 981 packages from CRAN, but we also have 135 packages from Bioconductor itself. So you can see that CRAN dominates Bioconductor as the source of origin for your repository, for the packages itself. So, some strengths. First of all, R is platform agnostic. You can run it on various architectures, you'll be fine. You have great interfacing with different languages, for example, the RCPP package for C++, and the R Java for Java. A lot of packages in R are actually written in C++, and this means that it can be orders of magnitude faster than writing the libraries in R itself. So shaping the data however you like into whatever structure. It is actually very easy to do in R. R has really, as the name suggests, it is a statistical language. It is made for this purpose. However, I consider this being perhaps quite trivial when you look at a language like Perl or Java, which is relatively easy to do as well. But are we actually near complete in Debian, given what is already available to package? And the answer is no. CRAN has itself 17,954 packages, so we have roughly 6% coverage with regards to what is in Bullseye right now. And indeed, I've left Bioconductor out of this because it is quite trivial and minute, in my opinion. But this is now R agnostic, so this is actually packaging related. How should we actually judge what is of importance to be included and maintained in Debian? And different people have different techniques, but one good heuristic in R could be for R packages, you base it on popularity, so downloads. And there is a nice package to do that called cranlogs. And essentially, you can use a code like this, to which for this example, I am looking at the Shiny package in R, and I'm looking at the number of downloads between this date to this date, and I'm forming a cumulative structure, to which I'm then graphing it using the ggplot2 library. And you can see this. So essentially, you can see that Shiny is quite a popular package. If you look at the rate of downloads, we're interested in the rate of downloads is quite high. So for me, this suffices as something that should be important and should be in Debian itself. But this does not come without flaws. Indeed, this introduces quite a lot of bias, because perhaps you have a newer and better package, or even a smaller package that's not got recognition, that is functionality-wise as good or better than even the most popular packages. So it's not a fair system, but at the end of the day, the most fair system is probably there being no system. So you should really package based on your own use case and what you think is right for your workflow. But this is one of the few techniques I use for myself when it comes to packaging. I do look at popularity, but indeed your mileage can vary. But it's a good thought to put out that cranlogs does exist. So what would I like to see in Debian R related? As a few people know, I'm definitely going to mention Shiny Server. Shiny Server essentially hosts Shiny apps, which we saw the sort of trend in the cranlogs example. It is already in Salsa, but it is missing some dependencies, essentially a chain of dependencies. Node destroy needs a sponsored upload soon, but I'm hoping to work on HTTP proxy, Node.js package as soon as I have spare time, and hopefully upload that. And indeed, you can see that using my analogy, we can sort of build a preference list that we should consider. But of course, this is not an exhaustive list. So second point or package to consider is MCViz, which is fairly new, but a little bit of a background to MCViz. It generates graphs which show causes of multicollinearity. So what does that mean? Suppose that you have in your dataset predictor x1, some variable x1, which is strongly correlated with two other predictors, so let's say x2 and x3. Then we say that multicollinearity exists between x1 and the other predictors. So MCViz essentially detects this sort of relationship, and builds a really nice, neat graph, which I quite like to use. And packaging this is actually quite trivial, so it shouldn't take too long. But most importantly, I would like to see RStudio in Debian. The RFP dates back to 2011. There hasn't been any more progress. From what I've seen, the progress is stalled due to the volume of dependencies within RStudio and also its volatility. But personally, I find RStudio in Debian quite of use, so it would be quite nice to collectively shift some time and effort into maybe seeing if we can get some gears moving again. So enough of R. Now we focus on Python. So Python is another language that's used in data science. It is a powerful language, and it's used predominantly in machine learning from what I've seen. And Debian itself contains 3,657 Python packages in Bullseye. But understanding this coverage is more difficult with Python because libraries are sparsely spread on the internet. So with R, you only have, well, apart from there being GitHub, most packages do make it into CRAN, some make it into Bioconductor, and then you have maybe a couple of other sources that we usually don't pay attention to. But with Python, there's more packages I find on GitHub that have not made it into a repository, such as PyPy. But PyPy itself is quite big. It has 319,174 packages in it. So there is quite a lot of room for improvement in terms of what we have Python-wise, library-related on Bullseye. And hopefully we can boost that number up by the next stable release. So some top Python packages. Again, I used the UDD for this, but essentially NumPy, great, because NumPy is heavily used in data science. It introduces arbitrarily sized matrices, but also it opens up a whole host of mathematical functions to operate on these matrices and set arrays. There's a lot of linear algebra functions. You also have the useful Fourier transform, the eigenvalue and eigenvector calculations, and you have quite a lot of other functions at your disposal. It is BLAS and Laplace reliant from how it is programmed, so this is accessible through OpenBLAS, MKL, which is Intel's, I think, and also Atlas. So this means that operationally it makes use of the platform it's on, and CPU-wise it is very efficient compared to one that does not use BLAS or Laplace. Now, second library that's also in Python that is heavily used is scikit-learn, which is a machine learning library. Although it is only ever good for classification, clustering, and regression, even dimensionality reduction, which is which is essentially mapping from a high-dimensional data into its principal components. So this is called principal component analysis, but not going into not rambling on into that topic. But essentially, I don't think it has good GPU support because it's not really intended as a deep learning library. But it is heavily reliant on NumPy, which is good. Again, we make use of BLAS and Laplace. So, what packages, Python-wise, would I like to see in Debian? First of all, I would like to see TensorFlow. TensorFlow has had brilliant progress. Some Basel-related issues still persist. Parts of the package still require tidying up. Unfortunately, TensorFlow Lite has had no progress. I don't think it's been packaged yet. But we are one step closer to seeing this in our next stable Debian release. Second library is TensorBoard, which is dependent on TensorFlow. And TensorBoard is on Salsa, but apart from the initial packaging, no progress has been made yet. So maybe we could shift some time or effort into that. But most of the software mentioned do make use of the CPU extensions, and these CPU extensions do actually accelerate computation. Notably, we focus on different SSC variants, and we focus on any purpose-made libraries for quite good, quite fast vector-based calculations. Again, we can use an accelerator like GPU to aid our sort of calculation speed and time. But we need to make sure, as software developers as well, that we keep the trend of not writing very cheap code or cheap code at all. And we really need to stick to writing high efficiency code that makes use of the platform it is running on. Fortunately, these days, there is a certain set of platforms. There is no 1,000 different CPU architectures that you have to recompile your code on. So we should really make use of the situation that we have. So and another thing to look at is actually softwares that relate to big data and data warehousing. Everything I've mentioned now is to do with computation, and indeed computation, data warehousing and big data elements in it do have computation, because you can run various queries on it, for example SQL. But indeed I think it's good to note that none of the Apache big data family is in Debian. Hadoop, which is a framework which allows for distributed computing of datasets across different clusters. This is fault tolerant software-wise, so you can run this on commodity hardware. Unfortunately, it is not in Debian. Likewise with Cassandra, it is a NoSQL distributed database, not in Debian. I have not seen Spark, which is a analytics engine, also not in Debian. So, just as a bit of a reminder as to what big data is, for big data we essentially consider this to be a data store and the facility of running queries. So big data can be thought of as data that is dynamic in nature. It is getting larger as time progresses, so we can say that there's high volume, high velocity, and high variability in the data. So we make use of a framework like Hadoop, which makes our workflow quite efficient and fast. But fortunately, this allows for distributed processing of large data sets across multiple clusters, aka the commodity hardware clusters that you can run with Hadoop. But indeed, Hadoop makes use of something called HDFS, which is a distributed file system. The last activity for Hadoop was around a decade ago. As for Cassandra, which I mentioned, it is on Salsa, but not in Debian. Spark does not seem to exist anywhere, but if anyone would like to correct me or maybe start contributing to that and getting it in Debian, that would definitely be much appreciated as well. So for 45 minutes, I would say maybe this is a short talk, but maybe I rambled on quite a lot. But nevertheless, many thanks for listening to my talk. Indeed, my email is in the bottom if you would like to discuss anything. I hope to continue my time on Debian for the foreseeable future. And I welcome any questions or feedbacks that you have regarding my talk and or the presentation itself. Thank you for your time.
Look, we haven't gotten any questions, but we have gotten a couple of comments. The first comment is by Andreas Tille and says, thanks a lot for working on Shiny server, and Yoast replied, I used might be able helping getting that into testing, and Tille said that would be a good idea.
I agree. As much we need as much people working on getting these sort of R packages into the next release. That would be great, especially Shiny server. It's sort of been out of release for a while now, so any sort of contribution towards it would definitely help out quite a lot.
And then Andreas Tille has 2 more comments. The second comment from him is, RStudio inside Debian would be a dream.
Yeah, I agree as well. I think from the link I posted to that RFP page, I think hasn't had activity for quite a long time. And as I mentioned in the talk, RStudio is quite fragmented dependency-wise, so we need to evaluate how we can get RStudio into Debian, because getting it into Debian would honestly be a dream as well for me, because I use RStudio quite a lot. So hopefully optimism.
And then we have one last comment from Andreas. TensorFlow would be a dream as well, hopefully becoming true a bit earlier.
So this has changed a little bit from when I last checked, but I believe I read on IRC right now that TensorFlow isn't new right now, so it's made it, which is great. So thanks a lot to all the contributors that contributed to such a huge package and made it get into Debian.
And then Don Fede is writing up the first real question. And he's done now. The question is, for someone newer with R star, can you describe some use case example that Debian users may consider with R? Or are these mostly for work, professional use?
Well, using any sort of language is not restricted to a sort of certain profession. However, R is known as a statistical language, and it's really good at doing statistical work and stuff. So statisticians and those in data science use R quite a lot because it has pretty good visualization, and you can sort of shape your data in really quick, easy, and efficient ways. Although if you wanted to do this in Python, you could. There is nothing stopping you. But R is, to be fair, anybody can pick up on it. And some of the graphs that you saw, the visualizations in my slides were done in R, specifically the ggplot2 library.
And then Paul has a question. When is TensorFlow going to be added to Debian packages? Is there any timeline?
So I think this goes back to when I mentioned TensorFlow seems to be in new already. So it looks like it's made it.
And then Kayla has a question or feedback. As an R Python data scientist, I'm accustomed to maintaining the libraries I need in my own local directories, where this breaks down and where perhaps distro level packaging can help mostly, in addition to thinking about popularity in downloads, is for those libraries that are for various reasons very cranky about userland installs due to dependencies.
Yeah, quite a lot of things that I've used in R I have to get from cran directly, and indeed it installs it locally, usually on the system. And I think this sort of evades with some of the R libraries I've used, the packages that I've used from cran. I find that in some of the cases they do break because the update is entirely down to that author or individual releasing it. So if we can sort of get it into some sort of stable ecosystem, such as within the next sort of Debian release, and we sort of freeze the versions of that, I think the sort of possibility of there being any sort of breakage would definitely be much lower. But for me, in my use case, I do sometimes install R packages directly into my sort of local onto my sort of local machine, and it does work for me. But I can understand there being many use cases where this wouldn't be some sort of a feasible solution.
And then Andreas Tille is writing another comment. You should contact the according team and tell your needs for packaging.
I may need some sort of.
No, I think it was a comment to what Kayla wrote.
All right.
Yeah.
I agree.
And that's all we got for now, in case no one types anything else. Now someone is typing more. What reason would you have to choose the Debian packaged R thing and not local install?
The same reason as why you would have a preference of using the Debian packaged R library as opposed to, sorry, let me rephrase this. So it's the same reason as to why you would want to choose some sort of Python packaged library in Debian instead of downloading it from PyPy and installing it via PyWheels. It's sort of the same ideology that if something works for you at a specific version, you want it frozen at that version until you can ensure it is stable. Although really, I think for me, it is sort of trivial. Nothing has really broken much in terms of local installs, but there are cases where, for example, the precision of numbers do change sometimes, depending on what has been modified in the next version of the library. And I know in sciences, specifically the sectors of sort of biomedicine, where high precision numbers are used quite a lot, this can obviously change the results. So being at a specific version ensures that the sort of deviation to what you expected doesn't really happen. And it sort of links with the comments down below, which I'm not sure who posted that. I think that's Andreas.
Yeah. Andreas commented or helped answer again. You have globally not user-owned installation. You have packages tested on Debian. You can install clusters easily by one command. Maybe bundling up sets of packages in some meta package.
Yeah, so this sort of act is more of like imaging what you already have and works for you, and you can replicate this across clusters. So you expect the same result from your library at all times.
And then use this writing more remark. Maybe reproducibility of scientific results will benefit from choosing Debian version 2 as opposed to the manual download Deb version.
Yes, and just to add to that remark, indeed, what you have in Debian at a certain sort of release, obviously people are going to be at that specific version unless you deviate from it with a local install. And being at that specific version indeed will mean that any sort of issues are rectified. So from a scientific standpoint, that should give you more of a peace of mind than just sort of blindly downloading one of the latest versions of some library straight from the author's repository, which is indeed not always a good idea, especially when it's to do with science. But I just also want to add that indeed reproducibility is quite a big issue, and I think this links to doing various tests with every sort of version increment you do, such as regression testing. But I know not every author does that, which is not good at all.
Now the etherpad.irc got silent again. Let's see if someone writes something. Doesn't seem like that. Thanks so much, Shayan, for the talk. And
Thank you,
everyone, for asking the questions.
Thank you for watching my talk as well and contributing towards the talks in IRC and Etherpad. Thank you.